Welcome to the second lecture of local cohomology. So in the last class we have revised injective modules and injective resolutions, and also we have seen I-torsion functor. So let me recall quickly what is I-torsion functor. So as before, you consider your base ring is commutative Noetherian ring with identity, and you consider an ideal I and M is an R module. Then I-torsion part of M, it is just collection of those elements of M that are annihilated by some power of I. Okay, so I power t times x equal to 0 for some t greater than or equal to 0. Now, in the last class we have proved that this I-torsion part we can consider it as a functor, because we can assign each module to its I-torsion part, and also we can assign each morphism f to the restriction map of f on gamma I of M. So this thing together it gives that a functor covariant left exact R linear functor. So covariant means it preserves the direction of the arrows, okay, and left exact means if you consider a short exact sequence like this, then you apply that functor, then again you will get an exact sequence like this. So exactness preserved on the left side. Okay, so it is left exact, and R linear means it preserves R linearity. So that means it preserves addition as well as scalar multiplication. Now one may ask the following question, that can we extend this exact sequence further? So that means can we extend it here? So this is the question, and again answer is yes, it is due to local cohomology. And today we will define what is local cohomology. So here is the definition. The ith right derived functor of the I-torsion functor, and this right derived functor of I-torsion functor, it is denoted by h I suffix I blank, is defined to be the ith local cohomology functor with respect to the ideal I. Okay, so this is the definition, and next we should recall how to construct right derived functor. So since it is a functor, it should assign each module M. So, and by definition this module, it is just defined in this way. You consider an injective resolution of M, and then you apply that I-torsion functor on that resolution, then you will get a quotient complex, and if you take its ith cohomology, then that is defined to be the this object, and we call it, this is called the ith local, this is just by definition of right derived functor, this is called the ith local cohomology module of M with respect to the ideal I. So here I should write that EM, it is an injective resolution of M. Okay, more precisely, if we write this injective resolution of M as follows: 0 goes to E0, goes to E1, goes to E2, so on. This is differential D0, D1, D2, so on. Then you apply that I-torsion functor on this. What you get, that is a quotient complex. This map is gamma I of D0, gamma I of E1, so on, gamma I of D1, yeah, so on. And then this ith local cohomology module of M with respect to the ideal I, it is defined to be the ith cohomology. And what is that? It is just kernel of the ith map. After applying this I-torsion functor, it is gamma I of di modulo image of gamma I of di minus 1. Okay, and this thing is true for all I. And so I should write that di is just 0 if I is negative. Okay. Yeah. So there is nothing before 0th position. So that means you can see that ith local cohomology module of M with respect to an ideal I, it is just 0 when your index I is negative. Okay, we will note it later. Yeah, so this is the definition for ith local cohomology module of M with respect to an ideal I. So you just consider an injective resolution and you apply that I-torsion functor. What you get, that is quotient complex, and its ith cohomology, that is defined to be the ith local cohomology module of M with respect to I. But we have defined it as ith right derived functor. So that means we should be able to assign each morphism as well, right? So it is second part. So I should write this question: what is this map for a morphism F from F M to N? Okay, so I will answer this question later. And also here we have defined this ith local cohomology module of M with respect to an ideal I in terms of this injective resolution of M, right? But we should prove that this object, it is just independent of the choice of this injective resolution. Then only it is an well defined object. So these two things we will prove later. But first we should see some examples. Our first example is that you just consider your base ring, it is set of integers, then any ideal, it is just principal ideal, you just consider a non-zero ideal. Then one may ask that what is this ith local cohomology module of Z with respect to the ideal I. We have seen in the first class that 0 goes to Q, set of rational number goes to Q mod Z goes to 0. This is an injective resolution of Z as a Z module, right? So then you apply, so this is 0th position, this is first position, and this is just natural projection map. Okay, and now you apply that I-torsion functor. So what you get, that is gamma I of Q, and this is gamma I of pi, gamma I of Q mod Z goes to 0. So this is a quotient complex, and again this is 0th position, this is first position, but we have observed in the last class that this is just 0 module and this is something non-zero, but since this is 0 module, so this map it is just 0 map, no other choice. and this is also 0 map. So this 0th local cohomology module of Z with respect to I, it is just kernel of pi, and since everything is 0 here, so this is just 0. And this first local cohomology module of Z with respect to I, it is again, this is kernel of this map, which is modulo image of this map, but image of this map, it is 0, so it is gamma I of Q mod Z. And we have seen this is just Z localized at P, and in other words we can write Z polynomial ring in P inverse modulo Z. This is something non-zero. And what about all higher local cohomology module of Z? And that is just 0 for all I greater than or equal to 2, because you can see that 2 onwards there is nothing, so everything is 0 in this portion. So 2 onwards all local cohomology module of Z with respect to I, that is 0. And in similar way we can, if you consider this polynomial ring, so this is polynomial ring in one variable over a field, so this K is a field, and you consider your ideal that is generated by that variable X, then in same way you can construct this ith local cohomology module of R with respect to the ideal I. It is just 0 if I not equal to 1, and this is K polynomial ring in X inverse modulo K polynomial ring in X. So if I equal to 1. Yeah. So, and this thing you can prove just by considering similar kind of injective resolution. So in this case I should quickly write it here, that just consider this injective resolution. 0 goes to the field of fractions of R, which is K round bracket X, that is just collection of all rational polynomials, and K round bracket X modulo K square bracket X, this as injective resolution of R. So as an injective resolution of R as an R module. So you just consider this injective resolution and you apply I-torsion functor, then that cohomology you can compute from here. Okay. And next we should see some properties of local cohomology module. So our first property of local cohomology module is this one, that HI, so this is ith local cohomology module of M with respect to an ideal I. This is 0 when your index I is negative. So this thing we have already observed, right? Moreover, each ith local cohomology module of M, it is I-torsion, it is an I-torsion module, that is its I-torsion part gamma I of H I, ith local cohomology module of M with respect to I, its I-torsion part, it is just whole thing. That means each element of that ith local cohomology module of M with respect to I, so each element there, that is annihilated by some power of I. So, and this thing is true for all I. Okay. So proof. So proof, it follows almost from the definition of ith local cohomology module of M with respect to I. So you can see that it is just subquotient of an I-torsion module. So this thing is I-torsion module. So let's say I equal to 1. So then this thing is I-torsion module. Okay. and at the first position cohomology, it is just kernel of this map. So first of all, kernel of this map, it is just submodule of this thing. Since this is I-torsion module, its submodule, that is also I-torsion, and in fact any subquotient, that will be I-torsion. Okay. So for I, this thing, since it is subquotient of an I-torsion module, so this is I-torsion module. Yeah. So just one sentence I can write. So this Hi, this is a subquotient of an I-torsion module. What is that? It is just gamma I of Ei. So ith injective module in the injective resolution. Yeah, so since this is subquotient of this I-torsion module, so this is also I-torsion module. Yeah. And our next property of local cohomology module, it is this, that if you consider two ideals I and J, so if both have same radicals, that is radical ideal of I, it is same as radical ideal of J, then this I-torsion functor, it is same as J-torsion functor, and once they are same, they induce same local cohomology. Okay. So hence that ith local cohomology functor with respect to the ideal I, it is same as ith local cohomology functor with respect to the ideal J. Okay. And this thing is true for all I. Yes. Yeah. Now we should prove this thing here. Yeah. So since radical ideal of I, it is same as radical ideal of J, there exist two integers m and n such that I power m, it is contained in J, and J power n, it is contained in I. Okay. And here both I and J, they should be finally generated, and which is true since we have this assumption that R is Noetherian. Okay. So here we need Noetherianness of R. So since R is Noetherian, both the ideals I and J, they are finally generated, and if they have same radicals, then you can prove that there exist two positive integers m and n such that you have these containment relations. And next, using this, we will prove that then for any R module, m gamma I of m, it is same as gamma j of m. Okay. And how to prove this thing? So you just pick one element from here. So that means that element is annihilated by some power of I, right? But since you have this containment relation, so you can, using this, you can prove that that element will be annihilated by some power of j as well. So that means that element will be there. So using this containment, you can prove this containment relation, and using other containment relation, you can prove the reverse containment. So that means you can prove this equality, and it in particular it proves that both the functors, they are actually same. Okay. And once they are same, they induce same right derived functors, and that is ith local cohomology functors with respect to the ideals I and that ideal J. Okay. So this is similar property we can have. This is B. It says that if J is a reduction ideal of I, that is J is contained in that ideal I, and J times I power n, it is just equal to I power n plus 1 for some n. That is the definition of reduction ideal of I. So for some n greater than or equal to 1. Then also both the functors, they are same. I-torsion functor, that is same as J-torsion functor, and hence that ith local cohomology functor with respect to the ideal I, that is same as ith local cohomology functor with respect to the ideal J for all I. So proof is basically same. So I should quickly write this thing. So J, it is given that J is a sub ideal of I, okay, and from this one, so you can write J times I power, so J power m times I power n, it is just I power n plus m for all m greater than or equal to 1. Yes, so since you have J is contained in I, so any element, so again you can prove this equality. So any element that is annihilated by some power of I, that will also be annihilated by some power of J. So that means that element will be there. Okay, so you can have this containment. And again using this one, if you see that some element, if it is annihilated by J power m, then that will also be annihilated by I power n plus m. So you can have this containment. So that means you can have this equality. So both the functors are same and they induce same right derived functors. So in particular, ith local cohomology functor with respect to the ideal I, that is same as ith local cohomology functor with respect to the ideal J. Yeah, and this completes the proof of this second statement. Now similar, yeah, so another property of local cohomology, it says that if injective dimension of M as an R module, if this is D, let us say something finite, then this ith local cohomology module of M with respect to any ideal I, it is 0 for all I greater than D. Yes. Again proof, it just follows from the definition. So I should write that since injective dimension of M, it is D, so that means there is an injective resolution of M of length D, which is 0 goes to E0 goes to E1 goes to up to ED, and D plus onwards everything is 0. So this is injective resolution of M of length D, and you just use this injective resolution and you apply that I-torsion functor and you take the ith cohomology. Okay, so since D plus 1 onwards everything is 0, so ith cohomology from D plus 1 onwards it is 0. Yeah, so next use, yeah, construct for I greater than D, you will get it is 0. Yes. Yeah. So so we have studied 3 properties of local cohomology, but now we should come back to this point, that we have defined our local cohomology module in this way by considering this injective resolution, and So we should prove that it is independent of the choice of this injective resolution. And next thing we should prove, we should define we should define this morphism for a morphism f from M to N. Then only this thing will be a functor, right? So to prove all this, we need some preliminary results. So we will start with this proposition. Yeah, this proposition, it says that you consider EM and EN, these are two injective resolutions of M and N respectively. Yeah. Then the first statement, it says that so M and N, these are two R modules, and you consider one injective resolution of M, that is EM, and injective resolution of N, that we denote by EN. Then for every morphism F, let us say F from M to N, it can be extended to a morphism. Yeah, so it can be extended to a, I should write Cohomology map capital Phi from EM to EN. Yeah, so what I mean by Cohomology map, that is in terms of diagram, I should write here. So you just consider M, and here you have N. So from M to N you have this morphism F, and here I will write injective resolution of M, that is EM. Let us say it is E0 goes to E1 goes to E2, so on. And here you have E prime naught, E prime 1, E prime 2, so on. Okay. So this statement that every morphism F, it can be extended to a Cohomology map, that means that you can have, there exists a map like this from E0 to E prime naught. There exists similar map from E1 to E prime 1, there exists phi 1, so on. So there exists phi 2, so on, such that this diagram is commutative. So what I mean by that, so you come this way, it is same as you come this way, and this is true for each commutative diagram like this. Yeah. And such map, so this collection of phi 0, phi 1, phi 2, that such that this diagram is commutative, we call it Cohomology map. Okay. So here I should note this definition. So this is one terminology we want to use later, that such map phi, so such map from EM to EN, yeah, is called a Cohomology map over F from M to N. And second statement we have for this proposition, that any two Cohomology maps phi and psi from EM to EN over F are homotopic. What I mean by that, that is their difference it is it is null homotopic. And I should recall what is null homotopic. So in terms of, okay, that means there exists this collection of maps, let's say mu n from En to E prime n minus 1, and it is for all n such that so 0 goes to m, goes to E naught, goes to E1, goes to E2, so on. 0 goes to n, goes to E prime naught, goes to E prime 1, goes to E prime 2, so on. So here you have F, and you are considering two quotient maps. One is phi, another one is psi. So, and any two quotient maps, so this second statement it is saying that any two quotient maps, they are homotopic. That means their difference, this one phi minus psi, it is null homotopic. And what is the meaning of that? That means you so if you consider this difference, let me write it here. It is phi naught minus psi naught. This one is phi 1 minus psi 1, so on. This is phi 2 minus psi 2, and so on. And it is saying that, yeah, so we should consider, we should write 0 here. So since we are just considering these injective resolutions, okay. And this thing saying, this second statement, it is saying that in this situation you can have a map like this from E naught to E prime naught, and that is mu 1, and from E2 to E prime 1 it is mu 2, so on, okay. And from E naught to this it is just mu 0, such that you come this way, it is same as coming this way plus coming this way, okay. So in terms of maps, I should write that this difference phi I minus psi I, that should be equal to, yeah, so if this map is d naught, let's say d1, d2, and this thing I should write d prime 0, d prime 1, d prime 2, so on, then phi I minus psi I, that should be d prime I minus 1 compose mu I, okay, plus mu I plus 1 compose di, yeah, and this thing is true for all I greater than or equal to 0. Yes, yeah. So it is bit complicated, but the main idea is that in this situation, that when two maps are homotopic, that means their difference is null homotopic. That means if you have such kind of collection of maps such that you come this way, it is same as coming this way plus coming this way, then in this situation both the quotient maps phi and psi, they induce same morphisms on the cohomology level. So I should write this statement more precisely later. Yeah, but at least using these two statements, now we can prove that any two injective resolutions of an R module M, they are homotopy equivalent. Okay, so as a corollary, I have stated this statement in the first class, but here we can prove. So any two injective resolution, let's say EM and E prime of M of an R module M, they are homotopy equivalent. So first of all, what is the meaning of homotopy equivalent and how to prove this? So this thing we will discuss in the proof itself. Okay. So you consider this M, and from M to M you can have this identity map. Again you consider that module M. Okay. And here you consider your first injective resolution of M, that is EM, and this is second injective resolution, that is E prime M, and here again that first injective resolution. Okay. So from M to M, if you consider this identity map, then first statement it is saying every morphism it can be extended or it can be lifted to a cochain map on the on their injective resolutions. So using that statement you can prove that from EM to E prime M you can have a cochain map, let us say phi1, and by using same statement you can have a cochain map, let us say phi2, and that is over, so both are over identity map on M. But here these EM and these both are same injective resolutions, so that means from here to here directly you can have this identity cochain map on these injective resolutions. Yes. So that means this phi2 compose, so since both the diagram it is commutative, so this whole thing if you just consider this way or this way, this is commutative diagram. So that means this phi2 compose phi1 and this identity map on EM, so both are over this identity map from M to M. And next we can use this second statement that any two cochain maps that is over a same morphism, they are homotopic. So using, so I should write this notation, so this is notation that if two cochain maps phi and psi are homotopic, then we just denote that by writing phi it is homotopic to psi. So this is just notation we want to use here. So by previous proposition, second statement, we get that this phi2 compose phi1, it is homotopic to identity map on the injective resolution of M. And similarly, if you consider phi1 compose phi2, that is also homotopic to identity map, but in this case it is identity map on the second injective resolution. And that is so this completes the proof, and in fact that is the meaning of homotopy equivalent. So two complexes, they are homotopy equivalent if there exists one cochain map from the first complex to second one, and you have another cochain map from the second complex to the first one, such that their composition that is homotopic to the identity cochain map. Okay, and that composition phi1 compose phi2, that should be homotopic to identity cochain map on the second injective resolution. So that is the meaning of homotopy equivalent. So next we want to use this corollary to prove that ith local cohomology module of M with respect to an ideal I, it is independent of the choice of injective resolution. So to prove that, we need this proposition. So here you consider C and D are two cochain complexes of R modules, and both phi and psi from C to D are two cochain maps, then first statement it says that this every cochain map from that complex cochain complex C to D, it induces morphisms on cohomologies. That is we have this collection of map. Yes. So in terms of diagram, I can say that let's say you have this Ci goes to Ci plus 1. Since we are considering cochain complex, so indices will be indices we should write Ci goes to Ci plus 1 goes to Ci plus 2, so on. And here you have Di goes to Di plus 1, Di plus 2, so on. And something is cochain map, that means on each level you have map. Let's say this is phi, this is phi plus 1, this is phi plus 2, such that this diagram is commutative. And so here it is Di plus 1, so it is, let's say, D prime I plus 1. Yes. So for such cochain map, this first statement, it is saying that you can have collection of maps or morphisms on the cohomology level. So at this point you can see, at this point cohomology, it is just kernel of this map modulo image of this map. But since this diagram is commutative, so kernel of this map, it is going to via this map, it is going to kernel of this map. And similarly image of this map via via this map, again it is going to image of this map. So on the cohomology level you can have a map from I plus 1 cohomology to I plus 1 cohomology of this complex. So that is your first statement. And the second statement, it is saying that if two cochain maps, they are homotopy, then on the cohomology level they induce same maps. It is same as this one for all n. So and what is the meaning of that two cochain maps are homotopy? So that means their difference is null homotopic, and the meaning of null homotopic is that you have collection of such maps such that you come this way, it is same as coming this way plus coming this way. And so main idea here is that if two cochain maps, they are homotopic, then they induce same maps on the cohomology level. So I will leave the proof as exercise. So proof of this thing, I will leave it as exercise. It comes in basic homological algebra. And now using this proposition, we should prove that so this corollary, that you consider ith local cohomology module of M with respect to an ideal I, it is independent of the choice of injective resolution of M. So you just consider two injective resolutions of M, one is EM, another one is E prime M, and using both injective resolutions we can compute this ith local cohomology module of M with respect to that ideal I. How? Just you apply that I-torsion functor on both the injective resolutions, and then you will get quotient complexes, and then you take ith cohomology, right. So here we should prove that you use this injective resolution or you use this injective resolution. So up to isomorphism you will get same object or same module. Yeah. So here is the proof. So we know that in this case you can always lift this identity map from M to M to a quotient map phi1, and here you can lift it to a quotient map phi2, and you know that phi2 compose phi1, it is homotopic to identity map on M. Yes. So once they are homotopic, after applying this I-torsion functor, again they are homotopic. So you apply that I-torsion functor, then you will get gamma I of phi2, gamma I of phi1, it is same as gamma I of identity map on this resolution, and it is same as identity map on this one. And once these two quotient maps they are homotopic, one is this composition and another one is this identity map, and they are homotopic, so they induce same morphisms on the cohomology level. So that means on the cohomology level so taking cohomology on a quotient complex, that is also a functor. So using that fact you can, after applying taking cohomology, nth cohomology, it is just it preserves the composition. Yeah. So it is same as taking this. Yeah. So since here you are taking cohomology, for this identity map on the quotient complexes, here you will get identity map on the cohomology level. So you should verify here each and every statement. I am just writing it here. Yeah, and similarly, just by considering phi1 compose phi2, that is also homotopic to identity map, you will get Hn nth cohomology of this phi1 compose nth cohomology of phi2, it is same as identity map on gamma I of the second injective resolution. Yeah. And what is your injective? Yeah, what is this nth map? In Hn of phi1, it is just, so phi1 is just map here. Yeah, so you are just considering this portion. Yes. So and you are applying that. So here this is a map from Hn to gamma I of Em to Hn to gamma I of E prime M. Yes. Yeah. And this is your, yeah, so I should write that, so these two things, this one and this one, it gives that this is an isomorphism. Yeah, this is an isomorphism, and this completes the proof, because what is this one? This is just ith cohomology module of M with respect to the ideal I when you consider this injective resolution, and this one is just ith cohomology module of M with respect to I by considering this thing as injective resolution of M, and both are isomorphic. So that means this object, this one, whether you use this injective resolution or this injective resolution, so you will get same object. So it is independent of the choice of injective resolution of M. Yeah, and next we should prove this thing, that how to get this map. Yeah, so this is definition. Yeah, so you consider a morphism F from M to N, and then how to define. So what is, again I should write that question, what is this map? So this should be a map from the ith, this should be a map from the ith cohomology module of M with respect to I to ith cohomology module of N with respect to I, right? Yeah. So we define that map in this way. So you consider M and N. From M to N you have this morphism, and here you consider any injective resolution of M. So let us say it is E0, E1, E2, so on, and here it is E prime naught, E prime 1, E prime 2, so on. So using the proposition we have stated earlier, we can lift this morphism to a map like this, phi naught, phi 1, so on, phi 2. Okay. And next, so you just consider this, yeah, that means on the injective resolution, from injective resolution of M to injective resolution of M, you can have a quotient map like this. This is just collection of this phi naught, phi 1 and phi 2. And then you just apply your I-torsion functor. It is after applying that I-torsion functor, again you will get a quotient map. Yeah. And that quotient map will induce morphisms on the cohomology level. So on the cohomology level you will get gamma I of yeah. So this map we are defining as this one. So I should write that define Hi of F as Hn of gamma I of phi, this quotient map. Yeah. And here we should now prove that this is independent of the choice of this quotient map. So you can lift this morphism F to many ways, to a morphism or to a quotient map from injective resolution of M to injective resolution of N. So that means you can have, yeah, so here I should prove this corollary, yeah, this corollary, that Hi of F, it is independent of the choice of phi. What I mean by that and how to prove this statement. So here is the proof. So you consider M to N, and here you have Em, here you have En, so here you have F. So suppose you have two quotient maps, one is phi, another one is psi, and both phi and psi, they are over F. So we have proved one proposition. So we have seen one proposition that any two quotient maps that is over a same morphism F, they are homotopic. So this thing implies that phi it is homotopic to psi, and that implies that after applying this functor again they are homotopic. So you should recall again and again these terminologies, that what is quotient map and what is the meaning of that two quotient maps, they are homotopic, and after applying any functor on these quotient maps, if two things are homotopic, then after applying that quotient any functor again you will get two quotient maps, they are homotopic, and once they are homotopic, so they induce same morphisms on the cohomology level. It is same as and this thing is true for all n, and that will complete the proof of this statement, that this map it is independent of the choice of these quotient maps over F. So this will be our last proposition for today's class. It says that you apply this functor on an identity map from M to M, what you get, that is identity map on M, and this thing is true for all I. This is your first statement. Second one, it says that you consider two morphisms. One is F, let's say F is from M to N, and G it is from N to L, and then you can take their composition. So after applying that local cohomology functor on this composition, you will get this one. So that means it preserves the composition law. This is again for all I where these are morphisms. And third one, it also preserves R linearity. So Hi R1 F1 plus R2 F2, it is same as R1 Hi of F1 R2 Hi of F2 for all R1 R2 the elements of R, and both F1 F2 they are morphisms from same module M to N. And how to prove this proposition? Again, it follows from the construction. Okay, so for example, we can just prove this second statement. So here you consider M, N, and L. So from M to N, you just consider F, and from here to here, you consider G. Okay, so and suppose EM, it is just injective resolution of M, and this is injective resolution of N, this is injective resolution of L. So you can lift this morphism to a quotient map, let's say phi, and this is psi. So this phi is over F and this psi that is over G, then that implies that psi compose phi it is from EM to EL, it is over G compose F. So you just use this quotient map to compute this morphism, and taking cohomology, it is a functor, so you will get this equality. Yeah, so this is for the second statement. And third statement, it says that, yeah, again I can write that if phi and psi both are quotient maps from EM to EN over F1 and F2, then you take this R linear combination of phi and psi. This is also a quotient map from EM to EN. Then this is a quotient map over R1 times F1 plus R2 times F2. Yeah. And next you use this quotient map to compute this one. What you get, that is this one, because taking cohomology, it is a functor. Again, you can use that. So as a consequence of all this, at least we can write this one. It says that for every I, this I local cohomology, so this is a covariant R linear. Why R linear? Because it preserves R linearity, and it is functor. Why it is functor? Because it preserves identity morphisms, and it also respects the composition law. So it respects the composition law. Yes. So this is R linear functor from category of R modules to itself. Yeah. So I'll stop here.